Today we are going to talk about an interesting topic in math called calculus. Now, I know a lot of you might have already known the subject called calculus. The way that we are doing it is more of experimental and rigorous. It's more intuitive. I would like to paint an intuitive picture. Usually, the subject is taught in form of principles, like you're taught a couple of laws and principles, and it's like a rule set. And then you play with a couple of problems, solve hundreds of situations, and then you feel like, okay, I know calculus. But nothing is further from the truth. Calculus of all subjects is very ideological, very dynamic, very creative. And at least this presentation, I would like to tell you how fun is calculus, how fun is calculus going to be. Okay, so calculus majorly focuses on change. So, okay, let's focus on the other aspects of uh, math. For example, take geometry. What does geometry talk about? Geometry talks about shapes, sizes, spaces. It usually talks about spaces, right? Okay. Then what does algebra talk about? Algebra talks about x's and y's. There are a lot of variables. There are a lot of, we call it monomials, polynomials, and so on. Essentially, what it is talking about is there are a couple of variables or parameters given, and how are these parameters interlinked? How does this change, which are interlinked together? Uh, then geometry is done, algebra is done. Oh, one of the important facets is probability. What is probability talking about? Probability is the study of chance, right? For example, you are tossing a coin and you talk about how probable it is to get heads or how probable it is to get tails. Now, calculus is study of change. Now, you ask where everything is changing in universe, like for example, weather, your waterfall, like everything. The universe is dynamic in nature, so you can apply calculus everywhere, every situation that you can see in your life. In fact, love is also changing, so you can apply calculus to love as well. So, calculus, I would like to think of it as learning music. I mean, music is an expression of an emotion, right? But calculus is an expression of a situation. Um, it helps you to translate a real-time phenomenon, like what is actually happening, into a more conceivable language. For example, language itself is changing, right? I mean, the think about the act of talking, the act of teaching. This is all continuously changing. Uh, Now you can deploy calculus rules of calculus here as well. So, what is the origin story for calculus? Calculus is derived from the word, a Latin word, which means a small pebble. And initially, pebbles are used to count and do a lot of fundamental math, like simple arithmetic for that matter. And hence, I mean, it is one of the, if you know the principle of counting, how we counted in the ancient times, is using pebbles, rocks. So calculus comes from there. Now, essentially, in math, I mean, math is not alone for counting, but a major portion of math is dedicated to counting, right? So, yeah, take about calculator for that matter. Calculator, what do? You compute, you calculate, and hence the word calculus. It's also coming from there. So, what is the core insight, or what's the like a breakdown for calculus? How do you break down calculus? Calculus is basically you're talking about things which change. How do you study it? You break down the whole complicated process into many chunks, like smaller, smaller chunks. So you study change of a particular phenomenon in very, very small parts. Okay. Now, why study calculus? I think the answer is obviously very obvious. Wherever there is change, wherever there is a prediction necessary, what's going to happen next? Calculus is involuntary involved. You need not bring calculus. Calculus emerges out of the situation. So modern applications ranges from everywhere, from economics, finance, stock market, engineering, sciences, math, anywhere where there's a prediction necessary. In fact, these days, uh, subjects like sociology and psychology, we are reading a lot about neuroscience. We're talking about pop psychology. All of these include the study of calculus, the study of statistics very, very aggressively now. So calculus is it's a language. It's one of the most important uh, alphabet of the universe, I would say. Okay. So who started this whole idea of calculus? And it goes back to Newton and Leibniz. Now, Leibniz is not as famous as Newton, and this is a whole sabbatical in itself. You have to this takes up the whole uh, another lecture. So this is a whole lecture in itself. But let's start with Newton. You all know the famous story how Newton was sitting on a tree and an apple fell. That's a story we don't know, but this is the pop story that everyone says. And the question is, okay, he realized that there is some invisible force which is pulling the apple down. And then he looks up at the sky and sees the moon, and then he asks this question: why doesn't the moon fall down to the earth? Which is the stemming questions for all physics and structure and math. That's how he started calculus. So he wanted to break down this complicated problem in there is no expression for this yet. There is no language to explain the problem. Now he started developing the language for this problem, which turned out to be calculus. Now you should read upon it how Leibniz and Newton had a rivalry. Both have very similar ideas and very similar presentations, but Newton somehow got became more famous. Yeah, we will discuss about this in much detail. But I think it's Newton who came up with this idea of fluxions, Fluxions, which I've written here. You should read upon it. So, how Newton developed this, and we will discuss at the end. So, I would like to pose a problem, a philosophical problem, which involves calculus. Okay. So, this is called the Zeno's paradox. So, Zeno is a ancient Greek philosopher. He used to annoy people by asking puzzles and questions. So, he he formulated a paradox. So what exactly is a paradox? Paradox is a statement which is self-contradictory. Anything which leads to a logical paradox, and I have given you a couple of examples here. Square circle, or I would say a squircle. So what does it even mean? Is it a square or is it a circle, or which one is it? And the answer is it's none. It's neither a square nor a circle, hence a squircle. Uh, so there is one more example. The state sentence on the right is false and sentence on the left is true. Now, if you look which of the sentence is actually true, right? What is it leading to? So this is a logical contradiction, and a logical contradiction is called a paradox. Now, how are these linked to today's class calculus? We will look forward. So Zeno is a Greek philosopher. He's from 5th century, student of a very famous philosopher called Parmenides. So here is the argument. Now listen carefully. Now, ancient Greeks used to follow a unit called a stade. A stade is a unit of length, that's all. So for our convention, let's take 1 meter. 1 meter, just for example. So he posits that you start at zero and you reach one, right? You start walking from 0 to 1. The question he asks is, in order to reach one, you should reach half of a length, right? I mean, if you're reaching 1 kilometer, you should first reach half a kilometer, and then from half a kilometer, you will reach further and further. Now he says, now this from half to full, again there is another half, which is one fourth of the total length, and he keeps on dividing this. So he asks, I can divide this length from 0 to 1 infinitesimally, like literally infinitely. So 0, 1/2, and 1/4, and 1/8, or 1/16, 1/32, and so on. So yeah, he asks if I can divide this unit length into infinite number of divisions, which is finite in nature. How can a finite length be divided infinitely? This is first question. If this is true, and mathematically it's true, how are we walking every day? Like you're reaching from 0 to 1. But if you keep dividing this process, you will never reach one, in fact. In fact, you will reach to a point where there is no motion. You're not moving at all. See, to reach, this is what I found in here. To reach any distance or destination, one must cover half the distance. Then the remaining half distance is again divided into half, and the other remaining half is again divided into half, and this process never ends. And he asks, what does motion even mean in this particular instance? Are you even moving? This is a contradiction, right? You are technically moving, but it seems logically that you're not moving, or the motion doesn't make sense. How do we solve this problem? Well, this problem remained problematic for centuries. And there is a mathematical concept which solves this. And you're right, your guess is right. It's from calculus. It's called a limit. We'll discuss what it is. Okay. So, as you know, what we have done, we have divided this distance into powers of halves, right? One half, one fourth, one sixth, one eighth, 1/16, and so on. So, what I've done is to write this expression in series: one half plus one fourth plus one eighth plus 1/16 plus so on plus 2 per n, because it's increasing with a exponent of 1 over 2 per n. Now what I would do is to multiply, and this is just a mathematical trick, and you will see why I'm doing this further. And I multiply the equation with 2 on both sides, which is 2 of the whole geometrical series, is multiply every term by 2, and then you get this unitary 1 plus all the infinite expression. And as you know, from the first line, like this itself is a geometric series. So I can write this geometric series in the following fashion. Now, what I have actually formulated, I have formulated, this is a very powerful expression, and we'll see further. From the unit length, I'm able to derive a geometrical series of this infinite expansion. Why does it matter, you ask? How? So if you keep on plotting, if you keep on, you keep what Zeno has asked, if you keep on adding the length that you actually, do this, like first you reach half and you reach one fourth, and then you add these both distances together and you get a certain number, and then you move forward again another half, which is one eighth, and you keep on doing this process. And I've graphed out a couple of points here. Okay, 0.75, 0.875, 0.9375. Do you see anything happening here? We are almost approaching 1. We are nearly closing on to 1, right? So, this is a very interesting concept in calculus. Limit is a what does limit actually tell you? Limit tells you what does it feel like to go or to reach this infinity, but not exactly reach the infinity. To get you an idea of what is happening here. So, if you keep on adding, it's like 0.9999 and so on. It is never 1, but you almost reach 1. Now, this is the mathematical solution, of course. And if you solve using infinite series, you'll get 1. Yeah. So Newton worked on a problem which is similar. He asked, uh, okay, why the hell is moon not falling in? And then he thought about it. We don't have any language to it. Uh, so he took the following problem. Imagine a car which is going up. I omitted a lot of details because it's outside the scope of the present course. But in a full lecture, I would love to discuss about it. But just take this question for instance. We are talking about how do we account for change, or how do we understand the concept of change initially, right? So imagine there is a car which is climbing up the hill, right? Now you say this car is moving, but how do we know? You compare it to one point to another point. So I have taken two different points here. This is point one and this is point two. And let's say this will give you a length, right? A slope of length L. Now I would like to study this. Now you try graphing it out, right? And you know what slope is. It's a rise over run. So how do I do it? Draw the perpendiculars towards the x-axis, which the first point is I'm consuming it as x, and it has moved h distance. right? So x plus h. Now the corresponding now this graph is what you're looking is you call motion or velocity. Now the what could the y coordinate? If the coordinate x is here, it is f of x, the function of x, right? So it's f of x and f of x plus h with consecutive points f of x and f of x plus h. Now, how do we take rise over run? It's change of y coordinates to the ratio of change of x coordinates, right? So what is the ratio of change in x coordinate, y coordinates? F of x plus h minus f of x, second point minus first point, which is the y coordinate, 2 to the ratio of change in x coordinates. What is change in x coordinates? X plus h minus x, which on cancellation will give you f of x plus h minus f of x by h. But what we would like to study is this h has to be very minute, right? That is exactly what's happening. In Zeno's paradox, this h is so minute, as you keep on going to infinity, you almost reach 1. So you should do this process infinitely. So we are calculating at every single small estimate on how this is happening. And this is the first principle of calculus. The concept of limit is so interesting that it doesn't, it shows you it's like a lens. I mean, the scenarios which you cannot normally understand or cannot handle normally, what it is to like to reach to them, what it is approaching. And when you solve it, you understand. That's how Newton solved the problem of gravitation. Yeah. So, what is the whole point of math? I mean, we are trying to understand a physical phenomenon. And since we don't have tools or language to express what's going to happen or how it's going to happen, we develop these processes, which is for example, let's say that there is a situation like you want to explain that I came yesterday. How do you communicate without language? So calculus is one small attempt to build the language for studying universe. That is what we do in math, right? We solve problems by understanding and developing new tools. So yeah, this is like an introduction to calculus. We will do much more rigorous work together once we start the course. I hope you join me. So, see you.